All right, so I want to do an example of an integral. This is from the table. This is sine of x raised to the mth power times cosine x raised to the nth power. And this first sentence about if m is odd or and if n is odd, these two examples, I just want to do an example of one of these, what you can do in this situation. So let me just try something. So let's do the integral of sine to the fifth power of x times cosine squared of x dx. Okay, and here's the idea. It's going to definitely, a really important identity is this Pythagorean identity right here, that sine squared x plus cosine squared x equals 1, right? I mean, this just comes from, let me just make a comment about this. It's called the Pythagorean identity because you basically have a triangle, a right triangle, and if this hypotenuse is 1 and this angle is x, then the base of the triangle is cosine, because that's adjacent over hypotenuse, right? And the opposite side is sine of x, because that's opposite over hypotenuse. And then the Pythagorean theorem, you just read off the Pythagorean theorem, and it says sine of x quantity squared, or we write sine squared of x, plus cosine squared of x equals 1. So that also means that if anytime you see a cosine squared or a sine squared, you can replace it, right? Because you could write sine squared of x is 1 minus cosine squared of x, or cosine squared of x is 1 minus sine squared of x. And so you get, as the more you do these kind of problems or any kind of problems involving sines and cosines, you just start to get used to, anytime I see a sine squared, I could replace that by 1 minus cosine squared if it was helpful, if it's helpful in the situation. If I see a cosine squared, I could replace it by a 1 minus sine squared if it's helpful in the situation. And here it is helpful because, it'd be nice in this example to do some sort of u substitution, like let u equal sine or u equal cosine. But then the problem is that you'd like a sine or cosine sort of by itself to be the dx, to be the du, sorry. So let me just show how that works here. Like in this example, you can sort of separate out one of the signs. Because it's an odd power, if we take away, sorry, that's not what I meant to do. If we factor one of the signs out, we can think of it, and maybe I'll just write everything in terms of powers, like put it in parentheses. So this is sine x times sine x to the fourth times cosine x squared, right? dx. And the idea is going to be that we can convert this sine to the fourth power because it's an even power, we can convert it all into cosines. So we're going to convert this term all into cosines. Sine to the fourth of x into cosines. As follows, right? So how do we do that? Well, we could say sine to x to the fourth. It's really like sine squared squared. So sine to the fourth of x is sine squared of x squared, which is 1 minus cosine squared x quantity squared, right? So I can actually rewrite this integral now as, do a couple things. I'm going to move this sine over here and group it with the dx, because that's going to be part of my du. And then I'm going to, write everything in terms of cosine. So this is 1 minus, so I'm just putting this sine to the fourth of x, 1 minus cosine, again, I'm going to write cosine x squared times cosine of x squared times sine x dx. And the reason I'm doing that is that you can see now, if you can let u be cosine, and these will turn into u's. And then we basically have a du. There's a minus, there's a negative you pick up, because when you differentiate cosine, you get negative sign. So let's take u equals cosine. So du is minus sine x dx. So this is minus du, this is u, this is u. And so this becomes the integral of 1 minus u squared quantity squared times u squared times negative du. And this is better because it's a polynomial. Still some work to do. You do need to like FOIL this out. You need to FOIL this out, right? This is 1 minus u squared times 1 minus u squared, which is 1 minus u squared minus u squared minus, so that's minus 2u squared plus u squared times u squared, which is u to the fourth. And so, and there's a minus sign floating around there. So this integral, we could write it as, maybe I'll pull the negative sign all the way out. This negative sign here, I'm just gonna pull it all the way outside. So we have 1 minus 2u squared plus u to the fourth times u squared times du. And now we can distribute this, multiply this through. And so that's really minus the integral of u squared minus 2u to the fourth plus u to the sixth, right? U to the fourth times u squared. You just add the exponents. Or the way I think about this is u times u times u times u times u times u, which is 6 u's. Okay, so then that's du. And now we can integrate this because this is just power rule, right? So this is minus 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus c. Let me just distribute the minus sign. That's minus 1/3 u cubed plus 2/5 u to the fifth minus 1/7 u to the seventh plus c. And now we plug back in for u. U is cosine, so we plug that all the way back in for all the u's, and we get minus 1/3 cosine cubed x plus 2/5 cosine to the fifth power, cosine of x to the fifth power, cosine of x, all raised, that raised to the fifth power, minus 1/7 cosine x. Cosine x is raised to the seventh power plus c. And that's your answer. So anytime you have an odd power, just to recap, this is your answer. You could check again. They get harder and harder to check the uglier they get, right? You could differentiate and check. It's a nice challenge to set yourself. See if you can get all the way back to sine to the fifth x times cosine squared x. If you did differentiate and try to check, you would probably use these identities a lot to change things into other things. But the point was, anytime you have an odd power here, like here, you can strip one off, strip this one off, group it with the dx, convert the rest into the other, like since we stripped off a sine x, since that was an odd power of sine, strip it off, convert everything else to cosine, and then the u substitution will go through. If it had been an odd power of cosine, we would have taken a cosine away, grouped that with the dx, and then converted everything else to sine. But notice it only sort of works for even powers because these only work for even powers. I mean, we could do sine x as the square root of 1 minus cosine squared x, but then you're going to introduce square roots into the integral. It's going to get horrible. So this is sort of a trick that works for just if either power of sine or cosine is odd. Okay, so that's the process. I'll do some more examples next, but I will stop this one there.